Assalamu alaikum. It's me Hammad Shaukat. Today's our second lecture of advanced electromagnetic field and waves. In this lecture, we will discuss about the electric field and their different perspectives, and we also discuss another concept which is Gauss's law. Okay, so first of all, for the case of electric field, as we did earlier, that when we are dealing with Coulomb's law and we find the force, Coulombic force, and now similarly we go further and have to find their electric field. So electric field due to some charge. Okay, so this is how we find in our previous lecture one. If you forgot to watch, please watch the first lecture, then okay. So this is the electric field which we find yesterday, that electric field is basically equals to the Coulombic force divided per unit charge. Okay, so suppose if there are two charges, q1 and q2. Okay, and q1 is the charge of which you have to find their electric field, and q2 is basically the test charge. Okay, q1 for which you have to find the field. So to find the field of q1, you must have to introduce an other charge, and that charge is so called as test charge, and the field and the charges of this test charge must be approximately equals to 0. This is why, because if the field of the test charge is also large, also much, so it disturbs the original charge field. So that's why for the case of test charge, you will take the field approximately equals to 0, very low. Okay, so when this charge comes in the it experience in q1, so it experience some electric field. So this is how we will find electric field is because basically equals to the Coulombic force divided by per unit charge. And force, Coulombic force of two particles we already find yesterday, it basically equals to k q1 q2 divided by the if there are two charges, then position square. Here the position is the original charge is x1, and the position and the other charge position is x, so that's why x minus x1 cube. This is all we find in our previous class, how to find Coulombic force of two charges. Okay, please watch the previous lectures first. Okay, so k q1 q2. Okay, divided by r square, and another it becomes cube, and 1 q2 is cancelled, so that's why electric field becomes equals to kq by this. Okay, this is if there are two charges. But what if there are n number of charges? Means if there are many charges. So if there are many charges, you just have to take this summation. Okay, k as it is summation 1 to n, means there are n number of charges, and qi is the number of charges, and similarly positions vectors x minus xi is the position vector divided by position vector magnitude cube. Okay, now there are two concepts, continuous and discrete. So when we are dealing with continuous, it basically means no gap. Okay, no gap. What it means, let me show you a graphical way. If there is a consecutive like this is a wave, so this wave is continuous. There is no gap between this wave. There is no concentric gap. If there is concentric gaps between some things, so you can say discrete. Concentric, so you can say this, again this 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 is force 1 2 3 4, so you can say this is concentric gaps 1 2 3 4. It not becomes to 10 again, so this is not, so this becomes discreteness, and this becomes continuous. Okay, so this is how electric field also behaves, like continuous and discrete. For the case of continuous, you just have to take the summation, okay, sum of all. So you can see if there are n number of charges, you just have to apply summation from I equals to 1 to n, so it becomes this. Also must understood about this, In the case of continuous, you have to divide your charge by volume and multiply it by volume. Why? Because charge per volume, it becomes charge density. As mass, as you know, mass divided by volume becomes density, and charge divided by volume becomes charge density, and this volume equals to the distance q. So this is in the case of continuous electric field in the continuous field. Okay, so now we can also construct like now you just have to put the value of summation I equals to 1 to n to qi in your main formula. Okay, when there are n number of charges, so this is the summation qi, you just have to put this, so it becomes k as it is, and summation qi equals to this, put this integral rho, which is the charge density, and dx cube, and similarly, and this thing as it is. So this is the electric field in the case of continuous distribution. Okay, let's continue in the case of discrete distribution. For the case of discrete distribution, it is quite difficult. So let us start. Electric field in the case of discrete distribution. Okay, so for the case of discrete distribution, we will have first an idea about Dirac delta function. Dirac delta function is basically, you know, that if this is a field, you can say, and there is a bump, and that bump, you can say, it is basically delta x. The bump is basically delta x, and at bump x equals to 0, and here x is greater than 0, and here x is smaller than 0. You must know, for the whole line, for the whole field, your Dirac function must be from minus infinity to positive infinity, and your Dirac function is always equals to 1 for the whole distribution. Understand? Okay. Also, the thing is that your Dirac delta function is basically an improper function. It is not a proper function. Okay, it is by nature. There are some properties we will discuss in our this lecture, and the properties are basically you can see when there is a Dirac function and the function is x minus a, and it becomes equals to 0 for the case of if x is not equals to a. Okay, moreover, there is another property. If you are taking your Dirac function integral from x1 to x2, okay, and your Dirac delta function is x minus a, it becomes equals to 1 when x1 is smaller than equals to a or equals smaller than equals to x2. Okay, and otherwise it is 0. Similarly, another property is that if you take another integral from x1 to x2 of Dirac delta function, and you have to introduce another function f of x, okay, it equals to another function which is f of a, which the distance you are taking, x1 is smaller than equals to a, smaller than equals to x2. Okay, this is how, because let's suppose if x equals to a, so a minus a becomes equals to 0, 0 multiplied by this 0, integral of this derivative integral of this is 1, and 1 multiplied by f of x means a, f of a, so answer is f of a. Okay, this is another property. Another property, if you will take the derivative of Dirac delta function, there is a derivative of Dirac delta function, you can see delta prime x minus a, and there is another function multiply and the same thing distribution over x1 to x2, then your Dirac function property is equals to minus of the derivative of that function, the position which you are taking. Another property which are not usually very important. So let's start further. Okay, now what you see here, that another thing I left before is that is the thing is in advanced electromagnetic field and waves, you use capital X for the notation for three dimension. Okay, here I choose another property. You see here that the delta function of X is basically position minus the three dimension is equals to n number of functions, x1 minus capital dimension 1, x2 minus capital dimension 2, again similarly x3 minus 3 dimension of third. Okay, similarly so on. Okay, for the case of discreteness, what you have to do, you have to take the summation. You have to take the summation as we did in the case of continuous. Similarly, you have to take the summation in the case of discreteness if there are n number of charges. Okay, so your Dirac delta will becomes now summation from I equals to 1 to n, and your charge n number of charges, it's basically the function, and it's multiplied with the Dirac delta function, and your Dirac delta function is um, delta x minus xi. Okay, this is for if there are n number of charges and that charges is distributed discretely. Okay, if you have three charges, then your distribution, then your delta function will become, you can see it divided into three parts. Like similarly q1 delta x minus x1 plus q2 delta x minus x2, similarly q3 delta x minus x3 for the case of three charges, and so on for n number of charges. This is okay. This is all about the concept of advanced electric field we discussed in this lecture. How to find the electric field of some charge, unit charge, by introducing another charge so called as test charge. By that charge you will find the electric field. If the field is continuous, we study how we find, and here if the field is continuous. Okay, and this is how if the field is discrete. Now another concept very important is the concept of Gauss's law. What is Gauss's law basically? Let me explain with the help of this short diagram. You can see here, let us assume you have a football. You have a football, and there is a charge in between that football, and football has many patches outside. There are number of patches outside the surface of the football. So let us suppose you have a charge q inside your football. Okay, and the distance between that charge to the surface of the football is basically the distance, which is denoted by r. Okay, and and that patch is the area of that patch is denoted as dA. Okay, and the angle between that patch and your charge is basically the solid angle. Okay, why? Because if you have a sphere and in between distance to the surface is always solid angle. Okay, and this is solid angle, so the angle is denoted by d omega, and electric field is going outside of the let's suppose football, and wherever there is an electric field there must be some unit vector, you can say area vector, and this is basically the area vector denoted by n cap. Okay, and the angle between the area vector and the electric field is theta. Now Gauss's law is basically the electric field is there is some charge inside a closed surface, and from that surface your electric field is going out of that surface, and you have to find that electric field. This concept is basically so called as Gauss's law. So the number of electric field lines passing through some unit area, okay, which is n cap, the unit area dA, and n is the unit vector, is basically equals to as you all know that the electric field is equals to kq by r square. This is the electric field, and n cap as it is, dA is the unit area of that patch as it is, and what this r cap means, r cap is basically the direction. This is not the r, we cannot cancel with this r because this is the direction. This is one unit vector, this is another unit vector, and you know unit vector has value 1. So 1 dot 1 equals to 1. You can say, you can write it at here as r unit vector, okay, dot n unit vector, and because it's a dot product, so 1 dot 1 cos of theta. So your r cap dot n cap basically equals to cos of theta. Now you just have to replace this here. The electric field passing through some unit area now becomes equals to kq. This product basically equals to cos theta, and dA as it is, and r square. Now this is your equation 1. As we introduce solid angle, so you must have to know what is basically the solid angle. So the definition of solid angle is the unit area divided by the distance square between them. Okay, this is basically the definition of solid angle. What is solid angle? Solid angle is basically the area, okay, area distance, unit area from which the field is passing out of that body divided by the square of that distance. So you know unit area is basically dA, and the square of distance is r square. So your d omega means solid angle becomes equals to dA divided by r square. Okay, now because you know, because it is the unit area, and unit area also we find that is also replaced by cos of theta, because r cap n cap is basically the unit vectors 1 dot 1. So 1 dot 1 basically equals to 1, so it becomes cos of theta. So that's why we introduce cos of theta, because there is some angle. You can see there is an angle between electric field and unit area, okay, and there is another angle between charge and the unit area dA, which is d omega. So that's why we introduce cos of theta here. So now your solid angle becomes equals to cos theta, your unit area dA divided by the distance square between them, this. Now you just have to do some replacements, okay. The replacement is that you can see here cos theta dA divided by r square. This is d omega, and d omega, so your answer is kq d omega final. So here I write that E dot NDA K Q D omega. Okay. Now simply put the value of K. You know K is a Coulombic constant and its value is 1 by 4 pi epsilon naught. So it becomes 1 by 4 pi epsilon naught Q D omega. So this is the Gauss's law. Okay. Simple form. K Q D omega. You can also 1 by 4 pi epsilon naught Q D omega. This is if there is a charge, but one if you have to find the complete surface, if there are number of charges on the surface of that sphere, so you have to take surface integral if you want to find the full surface charge distribution of the Gauss's law. Okay, you have to take the surface integral. So just take the surface integral of your electric field of your unit per unit area. So electric field, you know, we already find q by 4 pi epsilon naught, q by 4 pi epsilon naught, and you have to surface integral over d omega, which is the solid angle. Okay, because it's a solid angle and it's a sphere, so its value is 4 pi cancels with 4 pi, and you will finally get with q by epsilon naught. So this is the final form of Gauss's law, charge per epsilon naught. Okay, if you take whole sphere, okay, whole surface integral, whole this sphere, okay, has a distribution of charge per epsilon naught. But in that case, in the case of if your charge is inside the sphere, but if your charge is not inside the sphere, it is outside there, anywhere, anywhere, so then your charge distribution is zero. Why zero? Because if some charge is outside, it is going inward to the surface and then going outward to the surface, then its field become cancel each other and becomes equals to zero. So that's why whenever your charge is inside the sphere, then your Gauss's law then equals to the charge distribution, electric field distribution is equals to charge per epsilon naught. Okay, this is for the case of if there is one charge inside. Let you can see we suppose just one charge inside this sphere. So for the case of single charge, it becomes equals to q by epsilon naught. But when if there are n number of charges, you already know, you just have to use summation. Yes, exactly. You have to take this surface integral, means if there are n number of charges over all surface of that sphere, you have to take surface integral of your electric field per unit area. It's basically becomes equals to 1 by epsilon naught, and you have to take the summation of this charge because there are now n number of charges. Okay, so qi it becomes. Okay, you not take the integral, you just have to use the summation sign, because in the case of discrete, I already told you, you always use summation in the case of discreteness. Okay. Yes, for the case of continuous charge distribution, as I already told you, you have to convert, you have to multiply by delta V, means volume, and you have to divide your field by volume. Okay, so you can see this is the surface integral overall electric field per unit area. So it's already, it's equals to 1 by epsilon naught, 1 by epsilon naught. And now you have to multiply delta v by q and divide by delta v. Q divided by delta V, you already know what it becomes, charge density. So Q, when we divide it by delta V, it becomes charge density. And when we also multiply this by delta V, it becomes d cube x, means, okay, distance derivative q. So this is the final form of Gauss's law, integral form of Gauss's law in the case of continuous charge distribution. Okay, this is the form of Gauss's law. If your charges are discrete, you just have to sum up all your charges. But when your charges are continuous, you not use summation, you will take surface integral, and you will use charge density concept, and this is the integral form. Okay, there is another, now we are ending up to this lecture, and the last thing we will discuss about the differential form of Gauss's law, and this is so called as divergence theorem. Okay, simple is that, because uh, when a unit vector is multiplied by some magnitude of that vector, it becomes a vector. So this n multiplied by dA, it becomes dA vector. Okay, so now E vector, dA vector, both are same. Okay, no difference. So divergence theorem basically tells us as that E dot dA, because we are dealing with divergence, so you also know what is divergence of E. Let me explain you here. Divergence of E, divergence of E, what is divergence of E? Del dot E. This is the divergence of E, because we are dealing with divergence theorem. So your electric field distribution becomes equals to divergence theorem, because divergence theorem over the whole volume. So you will take dr cube volume over the volumetric integral. Okay, now you just have to put the value of E and compare. Let me show you here. Our your surface integral E dot dA. Okay, this is equals to volumetric, and again delta dot E, which is the divergence of that electric field, and D are Q. Now you just have put the value of this electric field, and you already know we find here the field value, this 1 by epsilon naught, so it becomes 1 by epsilon naught over the, you can see, integral over the volume. When in the case of continuousness, so it becomes volume and rho of x, and similarly you can see dq. Okay, means third derivative. Okay, simple, you have to write this simple as it's written, delta dot e drq. You can say dx cube if you are taking x position x to x. Okay, so this volumetric integral cancels with this volumetric integral, and this dx cube cancels with this dx cube. You will left with 1 by epsilon naught equals to del dot e, and you can say del dot e equals to 1 by epsilon naught. So this is, you know, the also the Maxwell form del dot e. So this is the divergence theorem of an electric field, which is equals to 1 by epsilon naught. And Gauss's law, you know, 1 by q, 1 by q by epsilon naught basically. Okay, you can say in simple words. This is how we already found. Okay, and there is another thing you can see here is a row which I left, so it becomes rho by epsilon naught. Okay, rho is basically the charge density. Okay, in the Gauss's law, you see there is also charge per epsilon naught if there are one charges. But what if there are n number of charges? Means there are many charges. So you will take charge density, the number of charges per unit volume. It becomes rho, and when you take the divergence of many charges, then your final result is charge per epsilon naught. Okay, so this is how you can know about the Gauss's law. And when there are one charge, or either if there are many charges, we see what's the distribution of electric field in the case of when the charges are discrete, and what's the distribution when the charges are continuous. Okay, you already know in the case of discreteness you always sum up all the distributions like we did in the case of electric field. But when you are dealing with the case of continuous charge distribution of either electric field, also if it is magnetic field, same procedure. Don't worry about for the magnetic field, all the concept and things are same if you are taking magnetic field. Okay, there is no such difference between electric and magnetic field. So that's all or for today's our lecture. And this is our second lecture of advanced electromagnetic and field and waves. So thanks for all, and thanks for watching. Stay tuned with us, and we will update you each and every lecture. Stay tuned with us and take care. Bye bye. Allah Hafiz.